Welcome to solverfy.
In this problem, we have light shining through three separate materials, each with different indices of refraction, N1, N2, and N3. In this diagram, we see that there are two possible paths the light can take in order to transmit into material 3. Because these paths have different lengths, in general, these two transmitted rays will be phase shifted one from the other. They want us to find what thickness L of this middle material will result in minimum intensity of the transmitted light, which means that these two rays will be phase shifted by half a wavelength such that they cancel out. We're given that the indices of refraction are N1 is equal to 1.6, N2 is equal to 1.4, and N3 is equal to 1.8. We're also told that the vacuum wavelength of the light is 632 nanometers. And specifically, I said they want us to find which thickness will result in destructive interference. Well, there's multiple thicknesses that'll do this, and they want us to find the second smallest thickness. So in order to get destructive interference, this extra distance traveled by this ray that's labeled R4 here, well, that distance is twice this thickness L, so that's 2L. Whoops. 2L. Well, that's got to be some half multiple of the wavelength, so we can write that as lambda, but it's not actually lambda vacuum because we're in this material, so it's lambda over the index of refraction, so that's the wavelength in the material. And it's got to be some half multiple of this, so we can write that as some integer m minus 1/2. Now we're almost done. We just have to check for two other possible phase shifts, because at the surfaces, if you're going from a lower index of refraction to higher index of refraction, the reflected ray gets phase shifted by half a wavelength. So let's check. The first reflection here, we're going from N2 to N2 to N3, and that's going to be 1.4 to 1.8, so N3 is larger than N2, so we get a half wavelength phase shift at this reflection. And then at this second surface here, we're going from N2 to N1, and that's also a smaller index of refraction to a larger index of refraction, so that's another half wavelength phase shifts. So two half wavelength phase shifts amounts to a full wavelength phase shift, which is the same as no phase shift. So this equation we have down here is correct. All we have to do now is solve for L, which just means divide by 2 here. It's going to be lambda times m minus 1/2, over 2 and 2. And since they want the second smallest thickness, well, the first smallest thickness is m equals 1. So the next one is m equals 2, so we have to plug in m equals 2 here. And plugging in all the values up here, we get that L equals 339 nanometers.